Welcome back to this course on statistical mechanics, and what we are trying to do here is to develop an understanding of basic phenomena from the point of view of statistical mechanics. And as I repeatedly tell that the undergraduates understanding, our undergraduate studies of physical chemistry is wonderful, going through all different phenomena which then finds use in biology, biophysical chemistry, in materials, in organic chemistry, all kinds of things that physical chemistry is sometimes called the soul of chemistry, but it is certainly the basic understanding of chemistry and also that branch of physics which interface with physics and chemistry. During my course and travel through the world, I found one very interesting thing, that what we studied in physical chemistry in universities of United States are that what we call physical chemistry, theoretical physical chemistry, liquids, polymers, and all other aspects of biophysics, protein folding, they are all studied in the physics departments in Europe, like in Japan, in not only Europe, in Japan, Europe, in France and Germany, they are very much in. So, theory of liquid is the physics department, and chemistry used to be the traditional chemistry, colloids, organic synthesis, things like that. The reason is that the understanding the physical chemistry or the things that you learn in undergraduates requires a lot of mathematics and the concepts which are very common and already existed in physics, like level equation I told you, which came to BBGKY, or the BBGKY, Bogoliubov and Bond, they are physicists. Iofon, physicist. Karkut was a physical chemist in chemistry department. Green was more of a physicist. Onsager was a physical chemist, trained as a chemical engineer. Then other great guys like Zwanzig, they are in chemistry department. So Stillinger is a chemist, and Isaro Hauman is a physicist. So this branch of statistical mechanics has physics and chemistry working together to unravel, to understand these rather complex systems. Now, we now start one thing. For next 40 minutes or so, we will try to do a very interesting thing, which is a big subject by itself. Just like in theory of liquids, there are books on theory of liquids, here also there are books on endless number of books on polymers. But our emphasis here is to introduce to students the concepts of statistical mechanics to understand polymers, and there are some beautiful work has been done, several Nobel Prizes have come. The picture that we have here is that of Paul Flory, and Paul Flory is considered the father of polymer chemistry or polymer physics, and we have this is chapter in my book in statistical mechanics, chemistry and material science, and we have taken this picture from his book. And Paul Flory, along with many other people, many other big names are there in that field, but he introduced the concepts of statistical mechanics, concepts of probability, and he modernized the polymer science. That is why one has so much. He got a single Nobel Prize for this, I think 1960s or 1970, sometime like that. And so, what we will do today is many of the things that Flory did, and he did pioneering contributions on the distribution of polymer size, end-to-end distribution of polymer, introduced the concept of excluded volume, which nobody thought will be so important and so interesting, and then he also went on to do a theory of sol-gel transition, and so that his stamp on the polymer science is really amazingly diverse, and he was both an experimentalist and the theoretician. He did many of the experiments himself, and he then developed the theory. So this was probably one of the last of those kind of gentlemen who did both in physical chemistry, both did theory and experiment. But of course, he had to be organic chemist also in order to synthesize these large polymers. Now we continue with Paul Flory's work. So, with millions of connected, so polymers are what we have, one have to remember there are millions. We are not talking of 10 particle or 20 particle things. We are the conventional polymers that we use on everyday, nylon and many other things, Teflon or rubber, all these things coming. There are millions and millions of monomers connected, and this is the natural playground of statistical mechanics. Because of this, note the term natural playground of statistical mechanics. That is a very, very nice way to put into it, because this completely many body system, these are statistical system, and there are some beautiful things that physicists talk about, like critical phenomena, where there is a long range correlation emerges, that density fluctuation in one region gets correlated with the fluctuation at a distance 1000 angstrom apart, that means 50, 100 molecules apart or 500 molecules apart. In polymer, there is already the correlation, because a polymer is a connected thing, but then one monomer knows another monomer which might be 10,000 monomer apart along the contour, along the chain, because they cannot cross. So, this excluded volume introduced by Flory introduced a long range correlation into polymer, which that is what later Pierre Dijon and Michael Fischer used the concept of critical phenomena to understand polymer science and polymer physics in a much detailed way. So, while Flory what we use the term polymer chemistry or polymer physical chemistry, what Dijon and Michael Fischer did was consider polymer physics, but they also do the same thing. So, it was initiated by statistical applications were initiated by Paul Flory, as already told. So, what Paul Flory did, and there are some other gentlemen also did, the end-to-end distribution. That means, if I have a polymer long chain, then it is very important to know what is the distribution end-to-end, because from that then I can get the size, and the size of a polymer is very important. It is not only measured in light scattering, that also plays a role in giving rise to the viscosity of the polymer solution and many other properties of the polymer. Okay. And then this effective interaction or excluded volume interaction was introduced by Paul Flory, and these remarkable many theories. It is one of the places where theory and experiment agree extremely well. Here is on us is a polymer is called random coil. This is random coil because they are connected, and even if it is a saturated polymer, means they are tetrahedral, one C connect to another C, but then because they are tetrahedral, so they beyond that point it becomes again another tetrahedral, but then this guy can rotate around this guy. So, by the time you have come 1, 2, 3, 4, fourth monomer, that it already has a very large number of configuration space. So, because of that, this distribution, end-to-end distribution has a huge number of configuration space it can access to. That is why you have to talk about distribution, and like in statistical mechanics. So, this is, so basically this what I said is described here, that if we start at one of them like this with this guy, then how you go around like that and come back. Okay, we start at A, then go low like that, from here going like that, then you get essentially beyond a point a random coil. So, if I want to know the position of a monomer nth of a specific monomer which n contour distant apart, then all I have to do is to sum over all the vectors. So, that is shown here. There I sum over all the vectors, and then I'll add this vector with this vector with this vector with this vector, and then if I have, then this vector. So, this if I add this vector, this vector, this vector, this vector, then I get that. So, if I want to get this distance, then I have to sum over all the vectors. That is very nice. These vectors are fairly random because of the tetrahedrality, because of the rotation around the bond. We call it backbone. and that gives rise to a wonderful thing, is that so I end-to-end distribution is sum over these things, and these are projections, and they can take many values. So, they are random numbers. Now, that is, now we have, if this distribution, end-to-end distribution is a beautiful things from central limit theorem and polymer size distribution. So, that should be the title, the central limit theorem and polymer size distribution, or polymer size distribution and central limit theorem. So, central limit theorem is something we discussed a little bit before, but let me state again that if I have a n number of random number, if value I have one variable x and x takes n number of distributions, or I have x n number of random variables which are taking all values within a certain range, and if I add them up, I sum, then if these my random variables which are weakly correlated or not correlated random number, then the sum becomes a Gaussian function. This is one of the most powerful theorem in the theory of probability, and that's the name central limit theorem. As I always tell in my class that mathematicians are not given to, unlike sometimes physicists, like theory of everything and many other things that we do, mathematicians are very conservative people. They are not used to giving very big names. They very rarely they say central limit theorem or fundamental, like they have a fundamental theorem of algebra, and that's the most important theorem of algebra, you know, that which gives you that a polynomial of degree n will have n roots, and that depending on the coefficients of signs of a and b, the complex conjugates and complex roots have to be in equal number. That is the fundamental theorem which is used everywhere. Whole complex analysis is based on that fundamental theorem. Similarly, central limit theorem is a hugely important in the theory of probability. It can be derived in many different ways, has been derived in many different ways, but we do not need that here. So, this is what is that if sum is all these numbers, then probability of S is this thing, is the Gaussian. So, that may have values between +1 and -1 randomly picked up. For example, in a way, the way we develop we generate a Gaussian distribution in computer, that we call a random number, and random number between say -1 +1, and then we add them up, and it is just about 12 such random numbers is enough, that n can be 12. Below 12 it does not work that well. Sometimes we take 20, but n equal to 12 will give you fairly good Gaussian distribution, and this is something which one should have. It is uniformly distributed between +1 and -1, then this average goes to 0, then you just have e to the power minus s square by 2 sigma square and the normalization constant in front. So, now coming back to polymer, in the polymer we all have this random, we are adding up. So, one bond, this one is really not that correlated with that one because it can rotate. So, if I think of distance between my central and the final one, then it is adding up these projections which are fairly random. So, then my central limit theorem, I can surmise that the end-to-end distribution is a Gaussian, and that exactly what holds down, and this is one of the most is not by n, can be even 12 is enough here, as I said in 12 is sufficient. And then we can continue a little bit to make it a little bit more as I said that it just angle cos theta I, angle make with that. So, if L is the bond length, as it is given here, theta is the individual bond vectors, then this theta I and cos theta I is random, just between -1 and +1 as I said, then R becomes, so it becomes L square, and then I get this is double sum and one of them gives you 0 or 1, then you this double sum become proportional to n. You can do it, this is a random number. Because one of them average word, then you ij with respect to that, and the rest one you can sum. So this should be capital N, this should be capital N, this should be capital N, this should be capital N. So one sum is taken care to give you this random number, second, and that's uniform distribution. Second sum gives you capital N. So R square, a beautiful thing, is an amazing result, amazing result. So root mean square, now I can say root mean square R square goes as n to the power half. This is one of the first result that is kind of known, though Florey systematized it. There are other people who have got this result, that size of the polymer scales as n to the power half. This we think is a remarkable result, because I think of is a remarkable result that root over R square, which is the size, is n to the power half L. And remember, our n, it can be 100 million, so 10 to the power 8. Then R square, the size, become 10 to the power 4L. Now L is 2 angstrom, or say 5 angstrom, then this 5 into 10 to the power 4 angstrom. That means it is 50,000 angstrom. So I now know the size of the polymer. This is very important, because that can be obtained by experiment. So we almost doing no work because of central limit theorem, almost doing no work other than this little thing that we have done, and that is trivial. So we get that, if they are correlated, that they are not, they are equal to 0, then only I equal to j survives, and that is a random number that give -1 to +1, that average. There should be probably a factor of half missing here, you get NL square. So we get this huge result because of the central limit theorem, and Florey did not do it by central limit theorem, he just took them a number and random numbers, and he used probability theory, but alternative way he arrived at the same, exactly same expression. So we continue. Then what is the probability if I have n a p n r is I hope these small mistakes are not in the book. This is the book, small and capital N mistakes. Okay, 4 pi 3 by 2 pi n L square 3 by 2. Okay, so this is number, as I said, this will be n r, capital R. So this is the full formula of the distribution of n number of end-to-end distribution of n number of, for example, if I do then I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then this is the 10, n equal to 10, this n equal to 10, and this distance, then this distance is the end-to-end distance. This is the R. So now this will give me, even if I told you if I have 20, then that's enough. Then the end-to-end distribution will be given by, all of us have done this calculation with the polymer, and we have found it out that this works beautifully well. Okay, to the extent that this is a universal, we consider it a universal formula, and the details of these bonds and the rigidity, all these things are not important as far, so far the form is concerned. There are certain changes in this rigidity and the kind of restriction on the randomness of the angles that is taken care by introducing a normalization, a kind of fitting parameter here. and that is the end of the distribution function things. So, now one important quantity which is the radius of gyration, which is comes in the light scattering and many theories, and radius of gyration is nothing but essentially same radius of gyration and moment of inertia that we find in classical mechanics. Like if we have 4 particles, then we find the radius of gyration is the take it as a central point, and then you want to find out what is the radius that this guy is rotating, and that is mass weighted from central, as I was saying, from central mass. So, this is the definition of the radius of gyration. So, when these things are we face that in classical mechanics, when these guys of different these are different mass, then we use this as the say if mass is the same everywhere, then Rg is thus just simply sum over Ri minus Rcm square. That means now I am going to take the distance, from a central mass. So, in a polymer I can go to the center of mass of a polymer, sorry. So, if that is such a polymer, then I can go and find out a center of mass here. Then now I want to do about the center of mass, what are the other guys are out, just like in the classical mechanics. Then that gives me from the center of mass how the size looks, and then that is this quantity, and one can show it is the same as this into comes out, because this is also a random number. These distances that I am considering are also random number, and then I again get the central limit theorem to get me this quantity, and again is a fact, except factor is different. I get Rg is 1 over root 6 Rg square. If I do not have that, then I have Rg square. Rg square 1 over 6 is a very famous result, 1 over 6 NL square. Rg square 1 over 6 NL square. So, basic thing is the same as the means square. So, Rg square. So, Rg square is same is as R square with the except numerical factor. So, the scaling remains the same. So, the size grows as root over n.